My name is Arnold Filtser, and today I'm going to tell you about scattering and sparse partitions and their applications. This lecture will be somewhat reversed in the following sense. First, without any definitions, I will go straight forward and show you the applications. And only then I will relieve the suspense and define this type of partitions, and I'll try to convince you that they're interesting and worth studying. So let's dive in. The first application is the universal standard tree problem. Here, we're having some center right point here, and in each point of time, the center wants to send some message to some subset of terminals or clients, the purple points here. Once he sees this set of clients, he can simply send the message using these, say, blue edges here. The cost of sending the message is the total weight of all the edges, which he used in order to send this message. With these purple points are fixed, obviously the optimal solution will be minimal standard tree spanning the center L all the clients. Now, in the next point of time, there will be arrived some new set of clients, and the center wants to send them again the message. So he can again pre-compute to compute the minimal standard tree and send the message using these blue edges here. So this is kind of the optimal solution, but from computational point of view, it's very costly. So of course we cannot simply compute the minimal standard tree. We can compute some approximation of it, but still, if we had a lot of different messages to send, it will consume a lot of time. An alternative solution is a universal standard tree. So here, we're given a single tree spanning the entire graph. So for example, the red tree here. And then once a set of clients arrive that we want to send them a message, we simply will send the message in the subtree spanning all these clients, the green tree here. And then when the next set of clients arrive, again, we'll simply send them the message using this subtree spanning them. So this is computationally very efficient because you can do it in distributional setting and in other setting as well, because it's very simple. You just have a tree and you're computing a subtree. However, it might be much worse than the optimal solution. And we define the stretch of a universal standard tree T as kind of the worst case performance of such a tree, which is the ratio, which you go over all the subsets K of terminals, and you look on the ratio between the induced solution by the universal tree to the optimal solution. The surprising part is actually that it's possible to compute a universal tree such that this ratio will be not very bad. And specifically, J et al. Showed the following. Suppose that the graph G admits a sigma tau sparse partition scheme, so I will soon define what this means, then you can construct a solution to the universal standard tree problem with stretch which is polynomial and tau and sigma times log n. Okay, so this is the first application. If you have sparse partitions, then you have good solutions to the universal standard tree problem. The next application I want to talk about is the standard point removal problem. So here we're given some weighted graph G, yes, and we have some subset of terminals K of size small k. This is fixed. And now the goal is to construct a new graph M with only the terminals at its vertex set, such that it will preserve the properties of the original graph in the two following manners. So first, we want to preserve the geometry of the original graph with respect to the terminals. That is, we want that the distance, so here by distance I mean the shortest path distance in the graph, for every pair of terminals T and T prime will be at least as large as the original distance in the graph G, and at most alpha times larger than the original distance. So this is in a sense preserving the geometry of the original graph. And secondly, I want that the graph M will be a minor of G. So this in a sense I want to preserve the topology of the graph G. So if G was planar, for example, the new graph M will be also planar. And the goal, of course, is to minimize alpha. So here's one example. Suppose that this star graph here always are 1, and this center point is standard point, which means it's not terminal. All the leaves are terminal. And the only way you can get the minor with only terminals as its vertex set is by contracting one of its edges. So we get this graph here. Now the weights must be at least 2, because you must dominate the original distances, and therefore the distance with T and T prime was originally 2. Now it's 4, so we have distortion of 2. And this is the best thing you can do. So if you would like, this is a lower bound of 2 for the standard point removal problem. So what is known? So we showed in the previous paper that give for every graph G with k terminals, you can construct a solution to the standard Partition removal problem with distortion logarithmic in k. The only lower bound is by Chant al, who showed a lower bound of constant 8. And this is all we know. So there's a gap between 8 and log k. So this is interesting. However, what's actually more interesting is what's happening with special graph families. So I mean, you want to preserve the topology. So in order for this to be like have some sense, you better have some special structure. So if, for example, your graph is planar, what you can say smarter about standard Partition removal problem, and actually we don't know to say anything smarter. The gap is still between 8 and log k. This is a major open question to resolve this, for example, planar graphs and other topologically restricted graph families. And what he showed in this work, so this is in a sense the main theorem of this paper, is that if every induced subgraph of your graph G admits a sigma tau scattering partition scheme, then you can construct a solution to the standard Partition removal problem with distortion which is polynomial in tau and sigma. Okay, so again, scattering partitions imply standard Partition removal solution to the standard point removal problem. So now it's time to relieve the suspense and finally define this type of partitions. So we'll start with sparse partitions. So here we say that the partition P, so this is like a partition, you divide all the vertices in the graph into clusters, is sigma tau delta sparse partition if, first, you want that each cluster will have diameter at most delta, and secondly, you want that every ball of radius at most delta over sigma, so this is kind of a padding parameter, how much you want to be smaller than the diameter of the graph, so you want that every ball of radius at most delta over sigma will intersect at most tau clusters. Okay, so we have three parameters here. Delta is the diameter, sigma is the padding, and tau is the number of intersections. And so you can see that this ball intersects three clusters, and this ball intersects also three clusters, and as well. So notice a single partition, there's no distribution here or probability. You want a single partition and you want it to succeed with respect to all the balls simultaneously, just all the kind of small balls will intersect at most tau clusters. Okay, we said that a graph admits a sigma tau sparse partition scheme if you can construct a sigma tau delta sparse partition for every diameter parameter delta. And the theorem by J et al. Was that if your graph admits a sigma tau sparse partition scheme, then you can construct a solution to the universal standard tree problem with stretch, which is polynomial tau sigma and log n. Okay, so yeah, note that I say diameter here, but actually it's not very well defined. There are two types of diameter people usually talk about. So first there's the weak diameter. So given a cluster A, the weak diameter of A is the maximal distance in the original graph between two vertices in A. And the strong diameter is the same, but instead you look on the induced subgraph of A. So you look on the maximal distance between two vertices in the induced subgraph. So for example, consider this cluster A here. So in the original graph, the distance between V and U is 2. In the induced subgraph, this is 6. And then accordingly, the weak diameter of A is 4. It's like this 4. And the strong diameter of 6. So they might differ. And actually, they might differ by a lot. So in this example, A is unconnected. So the weak diameter is some bounded number, while the strong diameter is infinity. Okay, so this is weak and strong diameter. And now in the definition of sparse partition, you can either say strong sparse partition or weak sparse partition with respect to the diameter guarantee. And similarly, you will have strong and sparse partition scheme with respect to the partitions you get. Okay, so note that actually J et al. Used weak sparse partition scheme. Yeah, so they say if you graph admit weak sparse partition scheme, then you get solution to the universal standard tree. But what they get as a result of using the weak sparse partitions is that the actual tree is not a subgraph. Yeah, so in a sense you get some tree, but I mean you cannot restrict it to only use edges of the original graph. So if you would like your tree to be subgraph, it's possible using a result by Bosch et al., who used some hierarchy of strong sparse partitions, but the results are much weaker, and actually there are some interesting questions here, which we unfortunately don't have the time to discuss. Okay, so now we move on to define scattering partition scheme. So this is very similar. Again, you have these three parameters, sigma, tau, and delta, and you want the following to hold. So first, you want each cluster to be connected, and secondly, you want that the weak diameter of each cluster will be at most delta. So in a sense, this is somewhat in between of strong and weak partition, in the sense because from one hand you want weak diameter, but from the other hand you want the strong diameter to be bounded, not infinity. Okay, so first you want this kind of strange diameter guarantee, and secondly, we want that every shortest path of length at most delta over sigma will intersect at most tau clusters. So note previously you want balls to intersect small number of clusters. Now you want shortest path to intersect small number of clusters. And again, sigma in the sense the padding parameter. I mean, what is the ratio between the diameter of the cluster to the path we care about, and sigma is the number of intersections. Okay, so you can see this path here intersect 3 clusters, this as well, 2 clusters, 3 clusters, and so on. Okay, so this is scattering partitions, and we say that a graph admits a sigma tau scattering partition scheme if for every diameter parameter delta you can construct a sigma tau delta scattering partition. And the main result of this paper is that if every induced subgraph of G admits sigma tau scattering partition scheme, then you can construct a solution to the standard partition rule problem with distortion tau, polynomial in tau and sigma. Yeah, so even though this is the main theorem of the paper, I mean, it's have some complications and we don't really have the time to discuss it. Instead, we will go and discuss the partitions. So we'll start by making some observations on the different partition and the relation between them, and then we'll go over different graph families and describe what type of partitions could be constructed, and we'll finish with some conjectures and open questions. So first, one can easily observe that if you have a sigma tau delta strong sparse partition, it's also a weak sparse partition. This is because, I mean, strong diameter is stronger than weak. That's it. Secondly, one can observe that if you have sigma tau delta strong sparse partition, then you also, the same partition is also scattering partition. And the reason is that every shortest path of length delta over sigma is included in some ball of radius delta over sigma. Yeah, so that's it. So in a sense, the picture of the world you have to keep in mind is the following. So we have scattering, weak, and strong partition. So every strong partition is also scattering and weak, but there might be some partitions which are scattering but not weak but not scattering, and actually even maybe scattering and weak but not strong. And we'll see examples of families lying in each one of these places. Okay, so let's start with discussing families. And the first family you can ask about is trees. So this is the most basic family. What about trees? What type of partitions could be constructed? So first, we observe that you cannot construct good, strong sparse partition scheme. Yeah, so you have some like bounds of tau with respect to sigma, and the reason is the following: you can construct a graph, a tree, with like high degree D tree, and then I mean the cluster cannot contain the entire tree, so it must end somewhere. So suppose this is the lowest vertex belonging to the cluster of the root, then all its children belong to different clusters. But because we require strong diameter, each such child should go to different cluster. Yeah, and therefore the ball of radius 1 around this vertex will contain d plus 1 if d is a degree clusters. So it's like breaking to lots of clusters, and this is quite bad. And you can actually put the parameters. This is what you get. So like 2 parameters you can keep in mind is, for example, if you want to preserve balls of radius at least like log n fraction of the diameter, then you must intersect at least log n clusters. And if you want something like smaller, that's already become quite exponential. So this is very bad, and actually this is as bad as Gellin graphs get. Okay, so this is strong partitions not working. From the other hand, you can construct very good scattering partitions. Yeah, so you can admit good scattering partition scheme, and the clustering scheme is very simple. So you first just construct a ball around the root, and then for each vertex out of with fuzzer in the cluster, which is a cluster, you construct a ball around it itself, and so on. So you will have the same issue as previously with small balls breaking to huge number of clusters, but it's not an issue because we care only about paths here. So if you have like a vertex here with all childs going to different clusters, you still can go only once inside, once outside, and that's it. So overall, you can intersect at most 3 different clusters. Okay. Next, one can also construct good weak sparse partition scheme for trees. And the idea here is that it's okay. So you might have this the same issue, but with this all kids separated from the father, But now we can put all these keys in one cluster because it does not need to be connected. So you can see this is not connected here, but still all these vertices have a common ancestor not far away, so they have bounded diameter and all working well. So this is great. So we can put trees here. So they admit scattering partition, they admit weak sparse partitions, but they do not admit strong sparse partitions with good parameters. Okay. The next family I want to discuss is the family of doubling dimension. So this, in a sense, we said that a metric space has doubling dimension D if every ball of radius R can be covered by at most 2 to the R balls of half the radius. This, in a sense, trying to generalize the Euclidean dimension, and indeed every Euclidean space of dimension D has doubling dimension asymptotically D. And we say that the graph has doubling dimension D if the induced shortest path metric has such dimension. Yet I'll show that if a graph has doubling dimension D, then you can construct a weak sparse partition scheme with parameters 1 and exponential D. So it's put them here, and we showed actually that you can construct strong sparse partition scheme with parameters both asymptotically D, which moves D to here. And note that this actually provides an exponential improvement in the dependence on D in the solution to the universal standard tree problem for this family of doubling dimension D. Okay, the next family I want to discuss is path width. So path width here is kind of try to measure how path-like your graph is related to tree width as well. It has an important role in the Robertson-Seymour structure theorems. And we show that you can construct good strong sparse partition and good weak sparse partition. And this implies, so if you have bounded path width, this implies that you can construct solution to the standard polynomial problem with dependence which is like constant or polynomial in row. This is the first family that we know to get some interesting solution about with some topological restriction outside the trees and some unpublished paper about alternative planar graphs. So this is quite exciting from my opinion. The next family is cactus graph. So this is, in a sense, a tree of cycles. This is kind of some weak version, I guess, of alternative planar graphs. And we get good scattering and weak partitions. However, they contain trees, so they don't have good strong sparse partitions. Next family is chordal graphs. This is graphs in which there's no induced cycle of size at least 4 without it. Yeah, that's it. No induced cycle of size at least 4, or every induced cycle of size at least 4 contains a chordal. And they're very different from trees because they, for example, contain cliques, but still they admit good scattering and weak partitions, and they also include trees, so there's no strong sparse partition. This is kind of the basic family. So note by example, it's interesting that you can construct a strong sparse partition for doubling metrics, but not for trees. But actually, there are trees which do not have any, which has unbounded doubling dimension. Okay. And the next family I want to discuss is this of Euclidean space. So even though it's infinite space, you still can construct partitions. So weak sparse partition is kind of clear because you have balls and you want to each ball takes a small number of clusters. And in this sense, actually, we show that you cannot do anything better than only use the fact that Euclidean space has bounded doubling dimension. This is in a sense the same bounds here. But from the other hand, you can construct very good scattering partitions. So what I mean by scattering partitions, so in Euclidean space, a shortest path will be simply an interval. This is a line between 2 points. And by using this kind of grid-like partition into cubicles, you can show that it's get one and like this scattering partition parameters 1 and 2D. And in a sense, if you look on what you can do with weak sparse partition scheme, so here you get 1. This the length of the path is equal to the diameter. If you want to get anything similar with weak sparse partition, the number of clusters you will intersect will be exponential in D. Yeah, so there's some separation here. So we'll put Euclidean space here, even though they are both depend on D, but there's a big difference. So to emphasize this difference, we put Euclidean space here. And finally, I guess the most interesting family we can think about in this context is this of minor free graphs. So using the famous KPR pilot partitions, one can construct R square and 2 to the R weak sparse partition scheme for minor free graphs, which put them here. But what about scattering? So we actually don't know. This is an open question, the main open question we leave. And what we conjecture that you can construct them. For example, for planar graph, I believe that you can construct scattering partitions with parameter constant. And know that this will imply a constant distortion solution to the standard controllable problem on planar graphs, which is a major open question. Okay, so we'll leave it as a conjecture. And the final family we need to discuss, of course, is that of Gellin graphs. So first, J et al. Showed that they admit log and weak sparse partition scheme. It follows by work by Kama et al. Implicitly that the Gellin graphs admit a log and scattering partition scheme. In this work, we combine these two results and show the Gellin graphs admit log and strong sparse partition scheme. So this applies this first two, and we also have a lower bound showing this is essentially tight, weak and strong sparse partition scheme up to second order terms. The only question left here, what about scattering partitions? So we don't have lower bound. We have some evidence that you cannot get constant. Yeah, but we conjecture that you actually can do better with scattering partition than with weak sparse partition. And what we conjecture that we can admit constant log n scattering partition scheme, and this is tight. So in a sense, you can construct paths of lengths about the length of the cluster diameter while intersecting only log n sparse partition, and know that like removing this O here, getting it the constant. Okay, so let's wrap up. So first, we discussed these two kind of connections between these applications to the type of partition. So J et al. Showed that if you have weak sparse partition scheme, then it implies a good solution to the universal standard tree problem. In this work, we show that if every induced subgraph admits good scattering partition scheme, then you can get a good solution to the standard approach removal problem with parameters polynomial in tau and sigma. We went and discussed these various graph families, put them all around this picture. And the open question is the following. So first, we conjecture that planar graph admit constant scattering partition scheme, which will imply a constant distortion solution to the standard approach removal problem. I conjecture also that for the family of 3-bit graphs, you should get some dependence only on K in the scattering partition scheme. And also we conjecture the general graph should admit constant log and scattering partition scheme. So for these two, I have very nice applications for the standard approach removal problem. But for this one, I don't have any like smart application, but I think it's a very natural problem to study. But that's it. I hope you enjoyed and go read the paper.